Welcome to Lecture 10, Energy and Climate. In the first 6 lectures, I laid the groundwork for an understanding, a scientific understanding of how planetary climates are established, and particularly how Earth's climate is established, ending up with the cycling of carbon, that all-important element that is establishing the greenhouse effect in Earth's atmosphere. The next 3 lectures, which we've just completed, looked at humankind's contribution to the global carbon cycle and to other properties of the atmosphere that result in greenhouse warming. So we've seen the science of climate, we've seen how human beings are altering the climate and understand that from a scientific point of view. In the last 3 lectures, we look at how human behavior might be changed in a way that could avoid some, at least, of the global warming we anticipate. And again, I'm not making prescriptions here for what I think human behavior should be. I'm simply making observations about what we are doing now and how those practices might change if we want to avoid at least some of the global warming. Some of it we can't avoid because we're already committed to it with the CO2 we've already put in the atmosphere. Well, why is this lecture called Energy and Climate? Because of all the things we human beings do that have the possibility to alter climate, by far the most significant is our consumption of energy. So in this lecture, I want to talk a little bit about how much energy people use and where that energy comes from, and what we get from that energy. And then in subsequent lectures, we'll look at what we might do differently. How much energy do we use? Well, that's a common question, but it's also the wrong question. It's the wrong question because the issue isn't how much energy we use, but how much energy we use in a given time. At what rate do we use energy? At what rate? How much energy do we use in a year? How much on average do we use every second? How much do we use every hour? We're really asking a question about the rate of energy consumption. And it's very common to confuse energy, a stuff, a substance, if you will, with the rate at which it's being used or produced or whatever. And that rate is called power, and that power is measured in watts. A watt is a rate of energy use. And you know what a watt is because you know what a 100-watt light bulb is, or a 1,000-watt hair dryer, or a 1,500-watt stove burner, or a 60-watt light bulb, or whatever. You have a vague feel for what a watt is. I'm going to quantify that feel quite solidly in the course of this lecture. But I want to emphasize that a watt is a unit of power. It's an amount of energy per time. In particular, in the metric system, the unit of energy is the joule, named after James Joule, and a watt is a joule per second. And that doesn't mean much right now, but I'll try to give you a better feel for what it means. So let me rephrase the question. At what rate does humankind use energy? And again, I'm phrasing that question because we're concerned in this lecture with how human beings cause greenhouse warming, and the dominant reason we do that is because we consume lots of energy. At what rate do we consume that energy? Well, we use energy at the rate of about 15 trillion watts. About 15 trillion watts. That's the equivalent of 150 billion 100-watt light bulbs burning. Now, don't ask me, is that a 15 trillion watts every year, or 15 trillion watts every hour, or what? It's not any of those things because it's already a rate. The word watt has that rate built into it. That 15 trillion watts is 15 trillion joules of energy every second. You can figure out by multiplying by the number of seconds in a year, which is approximately the number pi times 10 to the 7, by the way, to figure out how much we use in a year or in any other time interval you want. But that 15 trillion watts is a rate at which we are using energy on average, round the clock, all the time, the entire species. 15 trillion watts, the equivalent of 150 billion 100-watt light bulbs. Some other equivalents, there are lots and lots of units used to measure energy, a bewildering array of them. Different countries and different specializations use different energy units, and you just have to get used to there being several. So let me express that in several other ways. Frequently, energy is expressed in quadrillions of British thermal units. The British thermal unit is a unit of energy. It happens to be about 1,000 joules, not quite, but it's 10,1054 joules. So we express large-scale energy uses like of whole countries or of the world in terms of British thermal units per year, because again, we're talking about a rate. And that 15 trillion watts is equivalent to about 500 quadrillion BTUs per year. They're often called quads, 500 quads per year. The quad is a common unit you'll hear used for energy. A quad is a quadrillion British thermal units. A quad is equivalent to 500 quadrillion BTUs, 15 trillion watts, 500 quadrillion BTUs per year. They're equivalent to about 80 billion barrels of oil per year. If we got all our energy from oil, which we don't, if we got all our energy from oil, we would be consuming about 80 billion barrels of oil a year. about 2,500 barrels of oil every second. One, and there goes 2,500 barrels up in smoke. That's the rate at which we would consume oil if all our energy came from oil. In fact, we consume about 30 billion barrels of oil a year, and that tells you that our oil consumption is a significant fraction, not quite half, but a significant fraction of the energy we consume is in fact coming from oil. If you're a scientist, or if you like scientific notation, that 500 quadrillion BTUs per year, that 80 billion barrels of oil equivalent per year, that 15 trillion watts, not per year because the watts got the time unit built into it, the others are expressed as an energy per time, is also equivalent to 5 times 10 to the 20 joules per year, or 500 exajoules per year, if I can use the exa prefix, which means 10 to the 18. So it's about 5 times 10 to the 20 joules, or about 500 exajoules per year, 80 billion barrels of oil equivalent per year, 500 quadrillion BTUs per year, or simply 15 trillion watts. Those are all ways of saying the same thing, namely the colossal rate at which humankind consumes energy. Now, that energy is being consumed by roughly 7 billion people on the planet. So the energy per person, the energy per capita that we're using, is considerably a smaller number, but it's still big. That 15 trillion watts divided among a world population of 7 billion comes out to about 2,000 watts per person. And don't ask me, do I consume 2,000 watts every day or every year or what? Because that's, again, a rate. You, on average, as a citizen of the world, consume 2,000 watts. That's the rate at which you consume energy around the clock all the time. Now, I suspect most of the people in my audience consume far more than that, and I'll get to that in just a moment. But let me focus on that 2,000 watts a minute, because I want to look at that and compare it with the energies that our own bodies can produce. The human body, metabolizing its food, produces energy at the rate of roughly 100 watts. We're roughly equivalent to a 100-watt light bulb. And I want to give you a real feel for what that 100-watt number means. So what I want to do is do a little exercise here that will get you to feel literally in your muscles what 100 watts means. Now, if you've seen my course, Physics in Your Life, I had a hand crank generator there, and I got a teaching company employee to crank out 100 watts and light a 100-watt light bulb, and that teaching company employee felt exactly what 100 watts felt like. We're not going to do that. We're just going to use our bodies to produce energy at the rate of about 100 watts. So I'm going to do some deep knee bends. And if you're not driving in your car and are sitting leisurely in front of your TV and are suitably abled, why don't you get up and do some deep knee bends with me like this. We're going to go down about half a meter, about 18, 20 inches, and we're going to do that about once a second. 1, 2, 3, 4, up, down, up, up, down, up, down, up, down. I could keep doing that for a while, but I get pretty tired soon. My body is producing energy at the rate of about 100 watts. I'm not going to calculate that for you, but if you've had high school physics and know about kinetic and potential energy, you could probably do that calculation and come to the conclusion that we're producing energy at the rate of about 100 watts. Now, if you're a lot smaller than me, it's probably a little bit less. If you're a lot bigger than I am, it's probably a bit more. But it's somewhere in the range of 50 to 200 watts or something like that that you're producing if you're doing those deep knee bends. And I just argued that per capita, the world's population uses on average 2,000 watts, uses energy at the rate of 2,000 watts. And so what that means is the average human being on this planet is consuming energy beyond that produced by their own body, in fact, about 20 times as much as produced by their own body. So if you wanted to think about sort of energy servants that were working for you, doing the work of all that energy, every person on the globe has approximately 20 energy servants, that is, 20 human bodies equivalent worth of energy production going on their behalf. Now, that energy consumption is far from uniform over the globe. In the most energy-intensive countries, the energy consumption rate per capita exceeds 10,000 watts. Well, there's 100 hundreds in 10,000, so that means in the most energy-intensive countries, of which the United States is one, the energy consumption rate is equivalent to somewhat over 100 human bodies worth of energy per capita. You've got 100 energy servants working for you if you're in the United States. Since the average is about 20, that means there are countries that have far fewer than that 20. So it varies enormously. For example, in Australia, the average number of energy servants, if you will, is on the order of about 70 to 80. That corresponds to something like 7 to 8,000 watts, 7 to 8 kilowatts. In the United States, it's about 11 kilowatts, actually about 110 energy servants. In Saudi Arabia, it's pretty high. It's almost 80 energy servants. In Japan, it's about 50. In Poland, it's about 35 or so. It varies around the globe.